yeah, I think we can get started again. So now it's very nice to welcome Andreas Weiermann, who will give us a talk on functorial fast-growing hierarchies. And just real quick, maybe before, there was some interest maybe in having further discussions with Harvey and other online participants, and so maybe we can arrange for that after this talk if many people are interested in having more sort of informal offline discussions between the sessions. Okay, Andreas.
Yeah, thank you very much, Daniel. Thank you very much to the organizers for letting me speak here. It's a wonderful workshop. It's a wonderful place. I enjoyed everything very much. We have good luck with the weather. And so today I will speak about something which is maybe not mainstream in reverse mathematics, but somehow maybe a nice connection with reverse mathematics. And it has to do with so-called fast-growing hierarchies. Maybe some of you have seen them before, but they come with a new aspect, which is the functoriality. And this will be explained in the talk. So the talk is given by me and Fedor Pakhomov, and actually in Ghent I'm surrounded by a very nice group full of geniuses, and one of the geniuses is Fedor Pakhomov, the other one is Juan Pablo Aguilera, and I'm happy to be there and just to enjoy how everything works out. I will start with a general introduction. So this is low pace and everything is elementary. And I start with Hilbert. So what's the point here? So this workshop is also a bit on philosophy. And my starting point is a quotation by Hilbert, namely it is about the infinite. No other question has ever moved so profoundly the spirit of man. And I'm interested in the connection between the finite and the infinite. So the idea of this talk is to find new connections between the finite and the infinite, and moreover, this in connection with reverse mathematics. So we know already how to establish connection between finitary stuff and infinitary stuff. And one way is to deal with Friedman style, so-called Friedman style miniaturizations, using a sort of compactness argument, Victor's lemma. It's a great thing to arrange the transition between finitary stuff and infinitary stuff. And I'm also interested in Goodstein principles. So here is also a photo of Goodstein. Now the lower part of the slide is not so, yeah, it's readable over there, that's fine. So Harvey Friedman also initiated to consider reverse mathematics and so-called well-ordering principles. And this talk has also to do with well-ordering principles. And before, Girard initiated to look at the connection between reverse mathematics and certain principles regarding dilators. While reverse mathematics was not well, Girard was speaking about arithmetical comprehension, and he proposed a principle for dilators equivalent to arithmetical comprehension, but he was not really focusing on reverse mathematics. But you can read it in this way. Now, what are these well-ordering principles? So the first theorem is we look the first example, namely we start with recursive comprehension as base theory, and then we look at equivalences. And arithmetical comprehension is equivalent to the principle that for all sets x, if x is a well order, then 2 to the x, which is described by certain Cantor-normal forms, is also a well order. And this has been proved by Jeff Hurst in the context of reverse mathematics, but it's also in the proof theory book by Girard, written in a different context. And one can reformulate the second assertion in terms of what is called a dilator. So the exponential function is a dilator since the action of the exponential function on the natural numbers can be stretched into the infinite, and then you have the exponential function on ordinals. And now 2 years ago, we looked more into this. And so there was another equivalence due to Harvey Friedman, namely that over recursive comprehension, arithmetical transfinite recursion is equivalent to the principle that if you have given a well-ordering X, then you can set up terms for a formal set of terms using the Weiermann function. Let's say set for the terms smaller than phi x0 is a well-ordering. This is an unpublished result of Harry Friedman, and in the meantime, there have been published proofs of this. One was by Alberto and Antonio. The other one was by me and Michael Ratjen. And this was known for some years ago. But the new aspect here is that if you study the Ackermann function in more detail, you can make a functorial version out of it. And this is forming a so-called dilator. Now, what is a dilator? It will be explained in more detail later by Fedor, but I just want to give some sort of propaganda how these things fit together. And the Ackermann function can be extended in a functorial way to generate the Weiermann function, and that is basically behind this. And this has been studied now with Michael Ratjen, Anton Freund, Jan-Pablo Aguilera, and myself, and it has already been published. Now the next candidate in the list is Weiermann comprehension. And now some things become rather speculative, because how it is possible to generate such a complicated principle out of natural numbers. So that is, it looks that it's completely impossible to do so. But now the underlying idea is Girard in his proof theory book part 2, which is on his website, so it's not published, but it's somehow freely available as a PDF document. And Girard sketched an argument that Weiermann comprehension is equivalent to a certain property of what he called functor lambda, so that functor lambda preserves certain dilators. And Michael Ratjen showed in a talk in 2010 in Chicago a corresponding principle, but he was somehow more explicit how the objects look like. And that was a great talk in Chicago. And now, some years later, Anton Freund has really written down a fully fleshed out proof for this. And this is a principle by Anton Freund, namely that over recursive comprehension, Weiermann comprehension is equivalent to the principle that every dilator has a certain so-called Bachmann-Howard fixed point. And what we are going to do by now is we try to make a finitary version of the principle which has been proved by Anton Freund. Now, how is this possible? Well, we look back at Goodsein principles. Now, what are these Goodsein principles? Well, I will not explain them in detail. I guess you have seen the Goodsein principle for epsilon 0. So the standard Goodsein principle for exponential normal forms, so exponential normal forms of natural numbers, this is independent of the arithmetic and therefore independent of arithmetical comprehension. Now, in this article with Anton Freund, Jan-Pablo Aguilera, and Michael Ratjen, we also showed that there's a certain extension of Goodstein's principle, a more general, more dynamic Goodstein principle, and this is equivalent to arithmetical comprehension. Now, there's also Goodstein principle for Ackermannian normal forms, and this is independent of arithmetical transfinite recursion. And the more dynamical version is equivalent to arithmetical transfinite recursion. Now, how is it possible to go to Weiermann comprehension? Well, there's a Goodstein principle for the light-first version of Weiermann comprehension, and this has been proved together with Toshi Arai and Stan Weiner. There's some hope to use that one to generate full Weiermann comprehension. So the idea is the following. We use the fast-growing hierarchy indexed by ordinals smaller than epsilon 0, and they somehow describe the Bachmann-Howard ordinal, but as a sort of directed union, but in a static way. And the hope is, if we make it more dynamic, that we get a principle which is actually reaching Weiermann comprehension. And now I'm going to explain how this works. And I will just start at the beginning. So the fast-growing hierarchy, how is it defined? Well, we assume that we have a fixed countable ordinal big lambda, And let us just assume that this is epsilon 0, right? In the beginning, it's a nice example. Then we know what the fundamental sequences are. Then we can define the fast-growing hierarchy for it. So we start with the successor function. At successor stages, we define f alpha plus 1 in terms of iteration using f alpha. And if lambda is a limit ordinal, we use the fundamental sequence to define f lambda in terms of diagonalization. And then it's a classical result in proof theory that if Bjarne or S here 0 proves the totality of a function, the partial recursive function E with index E, then this function E is dominated by some function f alpha from the hierarchy. And now the surprising thing is, so you're speaking about a small fragment of reverse mathematics, and how is it possible to generate Pakhomov 1 compression out of these f alphas? It really looks more or less a mission impossible. For this, we need a function on ordinals, a sort of term complexity function, which is called norm function. What does this mean? Well, it's just a function such that, well, for given complexity n, there will be finitely many objects having complexity bounded by n. So that's basically what's written in the first line over here. And a typical example will be the maximal coefficient function. So if we have canton-normal forms for ordinals less than epsilon 0, so the maximal coefficient of 0, well, there's no interesting natural number at 0, so it's 0. And the maximal coefficient of a canton-normal form of this form is evaluated by taking the maximum over the finite coefficients ki over here, plus taking the maximal coefficients showing up in the exponents. So it's a sort of complex notion. But basically, we are looking for the biggest natural number showing up in the ordinal. This is not a norm function because the number of ordinals alpha less than epsilon 0 of maximal coefficient bounded by 2 is infinite because the omega towers have maximal coefficient 1. But if we fix to a fixed height, let's say an omega k, omega tower of height k, then it's a nice norm function. Now what's important here, you can intermix the maximal coefficient function with the fundamental sequences. So the property is, if alpha is smaller than lambda, well, the lambda x here converge to lambda, so there will be an x such that alpha is smaller than lambda x, and this x can be calculated, namely if x is bigger than the maximal coefficient of alpha, then this holds. It's a simple observation, an easy student's exercise to prove this. And since we have this property over here, well, we can use this somehow to come up with an alternative definition of the fast-growing hierarchy. Namely, the point is we abstract away from the situation of epsilon 0. So now we use an abstract norm function. And we define now f alpha of x using the norm function in the following way. So this new function f alpha is slightly different from the old function, but in this definition of f alpha, there's no longer any fundamental sequence. So we start with the successor function, and in case that there is a beta less than alpha of complexity norm of beta bounded by x, then we consider all functions iterations f beta of x to the x. We take the maximum over them. There will be finitely many beta less than alpha such that the norm of beta is bounded by x. So this is a well-defined maximum. So one has to be careful that this is the maximum of a finite set, but this is fine. It turns out that these two fast-growing hierarchies, the one with respect to the norm function and the other one with respect to the fundamental sequences, they are computationally more or less equivalent. Now, instead of the standard fast-growing hierarchy, I now use the binary fast-growing hierarchy, and I put the definition also on the whiteboard. So what is the difference with the F hierarchy? It's a successor stage, and instead of iteration, I just use composition. So this function grows a bit slower than the other one, but not much. So the result on provably total functions also works for the B alpha function. So B0 of x is a successor function, B alpha plus 1 of x is a composition of B alpha with itself applied to x, and B lambda of x is defined by diagonalization. Now the point is, the lemma on fundamental sequences I've shown before is important for the majorization between those hierarchies. So the idea is, if alpha is less than beta, we want to have that B alpha is eventually dominated by B beta. Now the question is, when does this happen? And the point is, we can calculate the x from which onwards this is going to happen. Namely, if x is bigger than the maximal coefficient of alpha, then this is fine. Moreover, there's a second interesting property. Given a number k, let's say 100 or 1 million, then you can ask question, well, what is the maximal alpha less than epsilon 0 such that b alpha of x is less than or equal to k? And the question is, can you calculate this alpha? Have you control over such alphas? And the answer is yes. If such an alpha is maximally chosen, and then it turns out that the maximal coefficient of alpha has to be bounded by x. That's a very important property, which is used in the later exposition when we move from epsilon 0 to a more abstract system of notations.
So this b is for a fixed x, right?
Yeah. So, well, at some moment, I don't know how much time I have. Otherwise, I could give a proof at some moment, but...
No, just to understand, parsing correctly the statement.
Yeah, the parsing for a fixed x and a fixed k, and then, well, I assume that this k is bigger than x. Otherwise, this alpha will not exist, so to say. But then I want to approximate the k from below using the x, and how can I approximate using the b alpha functions? And then I choose the alpha maximal such that b alpha of x is less than or equal to k. And if b alpha of x is still less than or equal to k, I could do the same thing, now replacing x by b alpha of x, and then I get b alpha prime, such that b alpha prime of b alpha of x is less than or equal to k. So I can form an approximation from below, and finally I hit the number k. And this is the important idea behind the whole construction. We will see it in a minute. Now,
how is the k in part B?
The k is arbitrary. So it looks a bit strange. It's just you have some k, and then if you have some, well, the point is it's sort of strange thing because the k does not show up in the conclusion.
Right.
Yeah, but it's this lemma is used when I approximate k using the b alpha functions from below. We will see in a minute where I use this. So it looks a bit like a statement which is not well formulated, but it's just some fixed k, x is given, and then I want to approximate from x, I want to come to the k, and the k has to be bigger than x, and then I look for the first alpha where this is going to happen, second alpha. So this works for epsilon 0, which works fine. But of course, it looks a bit mysterious. Anyway, it's just a proposition which you can prove, and it has a one-line proof, so it's not a deep thing. But the new idea is to abstract away from the epsilon 0 situation. I move over to the norm-based version of the b alpha function. Now, what is a norm-based version? Well, it's just as in the F hierarchy. So b alpha of x is, well, if there's no beta less than alpha, such a norm of beta less than or equal to x, I take the successor function. And otherwise, I look for all these beta less than alpha, such as norm of beta is bounded by x, and I take the composition of all of them, and then I take the maximum. Now, this new definition has a property that it fulfills these two properties 2 and 3 over there, just more or less by definition. Now comes the trick, namely we define notations for natural numbers smaller than b alpha n. And the idea is to set up a system of notations of finite numbers. So we have given a number n and the ordinal alpha. And all these numbers come with unique notations. And of course, when you just use the b functions, there will be many notations for the same number. So you have to figure out what are the side conditions. So, well, a number smaller than b alpha of n, of course, it could be a number m smaller than n. Or it could be the number n itself. Then I have here a vector which has length 0. So then k would be equal to 0. Or there would be a sequence of ordinals alpha 1, alpha 2, up to alpha k. such that the number is given by such an iterated function application. And the interesting new thing is that if I'm at time I plus 1, then the norm of alpha I plus 1 is bounded. So if I have here, let's say alpha k, the norm of alpha k is bounded by b alpha k minus 1 composed with b alpha n. And this is true for all I. And these conditions specify exactly in a unique way all the numbers smaller than b alpha of n. So this is now the proposition, and it's an easy proof to do so. So you just do half a page of an argument. So you prove this by induction on alpha. So if there's no such beta less than alpha, with norm beta less than or equal to n, then b alpha of n is by definition n plus 1, and then there's not much to do, because numbers smaller than n plus 1 are just the number smaller than n and the number n itself. Otherwise, b alpha of n is of the form b beta of n, and then we form two intervals, the numbers between n and b beta of n. For those we can use the induction hypothesis. And for the second half, we use an interval starting with b beta of n and going to b beta of n. And to both intervals, we can apply the induction hypothesis, and we are fine. It somehow, it just works by itself. Now the second thing is, which is also quite spectacular, you can compare these notations in a simple way. So we have a number smaller than b alpha of n. The numbers have the form iterate function applications. So the one number is this form, another number is this form. And now these numbers can be compared. Well, but they can be compared in an effective way. Namely, if we have these normal forms and this number is smaller than this number, if and only if this tuple of ordinals over here is lexicographic smaller than the tuple of numbers over here. So there's a very effective description. It's not just by magic, it's just you go into the terms, you do the lexicographic comparison, and it's the same sort of easy argument. You split your numbers into two intervals and you apply induction hypothesis to both halves of the intervals, and that's it. So, and this works not only for epsilon 0, it works for all definitions of the B function where one has a norm function available. Okay, that was a theory of numbers and notations for numbers smaller than b alpha of n. And this is a static environment, and now we have to make it dynamic. So finally we want to go to Pakhomov comprehension. Now how can this be achieved? Well, we now look into these Cantor normal forms, and we shift around the coefficients. So what is going on? We start with the function f from number L to number R. We assume that L is less than or equal to R, a strictly monotone function. And then if you have such a function, we move this monotone function to a function on ordinals, not on all ordinals, but the coefficient shift function for f moves Cantor normal forms where the maximal coefficient is less than or equal to L to Cantor normal forms where the maximal coefficient is less than or equal to R. And what you do is quite simple. You move 0 to 0. And if you have a Cantor normal form of this form, where the ki are smaller than L, you replace just the ki by f of ki. And you do this recursively also in the exponents. But basically, you go into your Cantor normal form, you look at the natural numbers, and every place where a natural number is showing up, you replace it by the shift. It's not a big deal. But now the point is, this gives a sort of definition of a functorial construction. Namely, the b alpha f function will induce a functor on natural numbers. And that's the point. Namely, functors on natural numbers, if you have these dilators, they move into functors on ordinals. And so it's very important to have a very effective description on the operation on natural numbers. And this is what we have. And this is the reason why everything works. So if we have a function from L to R, then we define a functorial situation. So we move the elements smaller than B alpha of L to the elements smaller than B alpha of R using corresponding operation B alpha of F. So in category theory, if we have a map from A to B, then the functor moves f of f from f of A to f of B. And this is what is going to happen here. So if we have small inputs, we just apply a function f. And if you have big inputs coming from numbers smaller than B alpha of L, they have this form. What I'm doing is I'm shifting just around the I'm shifting around the coefficients in the exponents, in the ordinals showing up over here. So if I have a normal form B alpha k, B alpha 1 of L, and I apply my function B alpha of F to it, what I'm doing is I obtain a situation. Oh, this k is wrong. This should be an R. So sorry for this. But for the rest, we just move, we go from the alpha I using our B alpha F function. We assume that it has been defined already on the coefficients. We move the coefficients upwards and they produce new ordinals alpha I prime. And these alpha I prime are showing up over here. And then using the result on unique notations and effective comparison of natural numbers, one can show that B alpha is a well-defined functor on the category of natural numbers, with strictly monotone maps between them. And that's basically what I want to tell about. And now comes the magic, namely we jump from the natural numbers to the infinite numbers. And this is will be done by Fedor. But then you have to move the camera, I guess. Yeah. Yeah. Or when you yes. No?
Okay, anyway.
Somebody then whose camera when you want to.
Okay, anyway, then I could just sit here anyway.
I should say also the second part of this talk is by Fedor Pakhomov.
Okay, yeah, thank you. Yeah, so let me continue then. Right. Okay. So Andreas have just defined this functor B alpha on the category of natural numbers and strictly increasing maps between them. Okay. So now let's go to let's say make this simple step to transform it. Okay. So let's consider the following. Okay. So we have this diagram. So like 0 is embedded into 1, 1 is embedded into 2, and so on. And the embedding is just like embedding its initial segment. And of course, if you consider a direct limit of this diagram, you get the ordinal omega, which kind of trivial. Okay, and now let's apply functor B alpha to this diagram, right? So then you observe the second diagram. So you kind of now B alpha of 0 is mapped into B alpha of 1 via the map B alpha of F0, F0, so this trivial mapping 0 into 1 as initial segment, and so on. Yeah? So you have this diagram, and then of course you could again take a direct limit of this. And in fact, so you'll need to learn a bit more to understand how it's proved, but basically the fact is, in fact, you will get a well-ordering by this construction. So this the direct limit of the second diagram is well ordered, and so this was denoted as B alpha of omega. And in fact, what you are getting is so if you take supremo over all alpha less than epsilon 0 of this B alpha of omega, then in fact you will get the ordinal known as Bachmann-Hobart ordinal. And so Bachmann-Hobart ordinal is ordinal of parameter with the proof theoretic ordinal parameter 3 pi11 comprehension. So the theory pi11 C0 minus that we have seen before. So we are getting, in fact, we are getting quite long orders there. Okay, so this is, and so we, of course, basically, if you apply B alpha for small alpha, then you will get some ordinals below this the bottom for ordinal. So in particular, you will get some, say, well-known ordinals like, say, epsilon 0, gamma 0, and so on. Okay, so yeah, so now, okay, so in the last slide we have seen this notation psi. So let's introduce this collapsing function. So this is like a standard way to define this proof-static ordinals of the strong series. Okay, and what I see here is actually this kind of the simplest collapsing function. So the name is function that collapses one uncountable ordinal. So it considers this omega capital would be just the cardinal omega 1, and then we define function psi from ordinals to ordinals by the following recursion. So psi alpha will be the least ordinal that is not a value of a term t, where t is a term built of 0, omega capital, omega x, so addition, and psi function, but there is a restriction that psi function could only be applied to ordinals less than alpha. Okay, so we kind of, when defining the value psi of alpha, we are referring only to values psi of beta for small ordinals. And this is quite clearly it's a well-defined function, and also since the
So what is x here? This is also supposed to be a term with.
Right. It just, I mean, you just could consider this omega 2x as unary function, a functional symbol. So, I mean, the term should be closed so that we could assign a value. Okay, so since the cardinality to set for Church's countable, it's quite easy to see that all values psi of alpha are always countable. So, because basically if you look at the minimal ordinal is not a countable set, that by necessity it would be countable ordinal. Okay, then you could see some calculations of psi function. So basically you get a bunch of well-known ordinals there. But let me skip this. Okay, so the goal will be to connect this function b with the collapsing functions. But before doing this, let's talk about the latest. Okay, so first of all, there's this notion of predilator. The abstract definition would be that a predilator is an outer functor on the category of linear orders that preserves full-backed and directed colimits. Okay, this is abstract definition. So if for people not familiar with category theorem that much, so I guess it wouldn't tell that much. So let's also give a more concrete definition. There is this special kinds of functor from category of linear orders to category and strictly increasing map to itself that we call denotation systems. And so basically what the denotation system is a phone. So we have the set C that we could consider like the C like this relativized notations. And then, so also you assign to each notation its arity, and then basically the image of the order A under this function D would be should be the set of this tuple. So you can, first component is C, and then you have a bunch of arguments, and the arguments should be taken from your order A. Right? So you can essentially, like the C behaves as a term on this final sequence of arguments, so that there is condition that arguments should increase. Okay, and then then the way how functum acts on maps should be aligned to this denotation, right? So basically, if you want to map C of A1 so on AN, then you should apply F to all the arguments. This is the way how the functor should act on act on maps. So okay, and in fact there is a theorem that actually, as the abstract definition before, is equivalent to this more concrete definition. And there are actually a bunch of, for example, we've seen before this denotation of ordinals below omega n using this Cantor normoforms. And in fact, so you could, so when you relativize this, so you kind of say that you kind of so basically you could say build up quite naturally the latest out of it. So you kind of relativize the denotation system to so that it could be applicable to arbitrary below. Yeah. Okay. So this is basically the idea. So the latest are kind of this relativized ordinal notation systems. Okay. Okay, yeah. So the next important point is about this weakly finite delta. So the delta is called weakly finite if it maps finite orders to finite orders. Right? And now, okay. So now we kind of we're doing the following. When we apply weakly finite delta to omega, then we could now obtain some infinite ordinal, of course. But the point is that from D we could recover norm function for the ordinal D of omega in quite natural way, because in fact D of omega is in fact just simply union of D of n for natural numbers n, and hence any element of D of omega appears in some D of n, and the norm will be just the least n where it appears. Right, so this kind of very natural way how you could construct a norm function from a weakly finite delta. Okay. Yeah, and so actually it's kind of important. So now, because now we will have this quite parsimonious situation where on one hand this weakly finite delta surfaces ordinal notation systems with a norm function, and on the other hand there will be this kind of functors on natural number, on the category of natural numbers, or furthermore the category of ordinal. So we can guess this dual view of this weakly finite delta, which is kind of crucial for this whole work. Okay, and yeah, okay. Now observe that actually B of D was a weakly finite delta. So okay, so actually first of all, what BD is? So we say that we denote as BD simply B of D of omega, and as we seen, if D was weakly finite delta, then we have a norm function for D of omega, and hence we could use the definition from that was presented by Andreas. And yeah, so hence we have D was weakly finite delta, then we have this function BD from natural to natural. Yeah, and so I just reiterate the definition. Okay, and yeah, so the crucial theorem is that this is well-defined function that extends to unique delta. Okay, so now let me give one alternative definition of BD. That will be given in terms of collapsing functions. So that you see that kind of this connection between collapsing functions and this fast-growing hierarchies. Okay. Yeah. So what we need to know here is this notion of support functions. So yeah, basically, so if you we have some order D of A, then you basically support of a particular element of the order is the set of arguments that we used there. Kind of trivial. Yeah. Okay, and now we're defining this order BD of A as this list by inclusion linear order that first of all contains a copy of A, and then it contains this formal collapsing expressions. So if you have this base 2 if you have base 2 counter-normal form, where your exponents are from the order D of BD of A, and there is this support condition, then so you could use this formal collapse of this counter-normal form in your notation system, and then we compare the collapses in the same way as we compare these counter-normal forms. Okay, and in fact, so we're having that it just that this definition, in fact, is the same as the previous definition in terms of in terms of this normal form for fast-growing hierarchy. So basically, the point is like this. So this formal collapse psi of counter-normal forms simply corresponds to this normal form using B function, right? So we can when you have B of alpha and so on, B of alpha 1. This basically translates to psi of 2 to the alpha 1 plus 1 plus 2 to the alpha m. Okay. So basically, like just one could check combinatorics, and combinatorics is exactly the same. So this is the same function. Yeah, and so okay, so now so this main theorem is that basically the following three statements are equivalent over RC0. So Weiermann comprehension. For every weakly finite dilator D, BD is a weakly finite dilator. And for finally that for any dilator D, BD is a dilator. So yeah, so this is the main theorem. Okay. So let me now. So how much time do you have?
Like 15 minutes.
Oh, okay, that's good.
Yeah.
So then let me then sketch some proofs. Actually, the proofs are all the proofs here are quite simple. So I think the main achievement of this work was really like find this conceptual definition that we can organize, but then the proofs are quite simple. Okay, so now first of all, let's show that indeed B maps dilators to dilators. So what we need to check for this? So we're given a dilator, we're given a value order A, and then we want to show that BD of A is also valid. So this is basically what we need to show that B is this dilator preserving operator. Okay, and we are using here Weiermann comprehension. Okay, so by Weiermann comprehension, we could find the well-founded part of BD of A. And naturally, our goal will be to show that a well-founded part coincides with the whole BD of A. And then we will be done. And here construction of well-founded part is like crucially uses Weiermann comprehension because, so now our proof proceeds by transfinite induction on elements of D of omega capital. And what we show by transfinite induction is that for any collapse of that is inside omega capital, if and alpha from D of omega capital, we could append this 2 to the alpha in the end of this counter-normal form, and still be inside omega capital. Okay. Yeah. So then the proof was quite simple. So if you have this, so basically we first show that if you then after we prove to this by transfinite induction, we show by induction on I that if so that if yeah, right. So okay, sorry. So basically, we need to show that we're given some arbitrary collapsing term from BD of A, and now we want to show that it's inside omega capital. And for this, by induction on I, we prove that its initial segments are from omega capital. Yeah, and this basically could be done quite easily using this previous proved induction statement. Okay. Oh, okay. So now let's. So let me explain how we obtain pi11 comprehension from this principle. Okay. So it works as follows. So we are using this principle by Anton Freund that Andreas mentioned. Okay, so the principle was that for any delta D and the Lord A, there exists this theta collapsing function. It's a slightly different notion of collapsing function, not basically it's quite, closely related. And there is this combinatorial property of theta that so if alpha is smaller than beta and support of alpha is less than theta of beta, then theta of alpha should be less than theta of beta. That's the first condition. And second condition is that support of alpha is less than theta of alpha. Okay. And the theorem of Freund was that the fact that for any delta and valor there is such a function is equivalent to pi1 comprehension. Okay, so now in order to prove that our principle implies pi1 comprehension, we will use it to construct such kind of collapsing functions. Okay. So for delta D, we consider slightly different delta F that would map A to the Lord A to this expression. So omega plus 1 of D of A plus omega. Okay, so of course one need to check this delta, but this is kind of triviality. And now we define the so what we're now doing is we are equipping the order D of B f of 0 with the collapsing function. So our choice of A will be BF of 0. Okay. And yeah, and so and then we simply define collapse as psi of alpha is basically as the least this Cantor normal form where the last so that would be in our order, and the last expression in this Cantor normal form should be 2 to the omega plus 1 times alpha. Okay. And then, in fact, one could quite straightforwardly check that, in fact, theta defined like this satisfies this conditions from Freud principle. Okay, so important. Sorry. Okay. So yeah. So important point here is that, of course, we used. Our principle here crucially for the letters that are not weakly finite, because in fact this transformation first of course even Anton so Freud's principle was formulated for arbitrary deltas, not just for weakly finite ones, and secondly this transformation from D to F maps deltas that are not that even are weakly finite to deltas that are not weakly finite. But this is not that big of a deal, because then there is a quite simple transformation that allows us to derive our principle for the case of weakly finite delta, for the case of orbit delta from the case of weakly finite delta. So essentially, given a delta, you somehow construct a weakly finite delta that behaves similarly to your initial delta, and then you could prove that this B of weakly finite of initial delta is delta using the fact that B of this corresponding weakly finite delta is a weakly finite delta. Okay. Okay, so in this talk, so we somehow talked about this so binary fast-growing hierarchy. Also, of course, the most standard one is usual fast-growing hierarchy. And so let me just explain what will be the difference there. And so, in fact, the choice wasn't particularly essential. So the behavior for binary fast-growing hierarchy and for usual fast-growing hierarchy is almost the same. And the only difference like that it becomes the slightly more technical details in the case of usual fast-growing hierarchy. So again, we will have unique representation systems for of usual fast-growing hierarchy. Again, I mean this norm-based version of usual fast-growing hierarchy. And the difference is now that you will have these exponents in here, right? So it's not B of just single application B of alpha, but then you'll have the exponent. And then you could reformulate this function in terms of collapsing functions. And now the difference is that before we collapse this base 2 counter-normal forms, and here we are collapsing base omega capital counter-normal forms, but essentially it's the same thing. And again, there's the same kind of results here. So okay. Okay, so the last thing that I want to mention is the following. So there is this classical theorem by Girard about the things called slow-growing hierarchy. And so, okay, so slow-growing hierarchy is elsewhere a natural hierarchy of this functions from natural to natural. So you start with G0 of x equal to 0, and then in each successor case you simply add +1, right? So you say just +1 of x is alpha of x +1. So this, of course, is kind of much weaker transitions steps than this, for example, iterating composition, as we are doing in binary fast-growing hierarchy. And then on limit stages you diagonalize. Okay, and the curious fact is that in fact, so this hierarchy is really quite misaligned quite a lot. So this, and so what Girard proved was that you get the order growth of f epsilon 0 only on Bachman covert ordinal. Okay, but that's kind of Girard needed to do quite a lot of technical work to achieve this. But so what I wanted to tell is that if you kind of using this view as of ordinal notation systems as D of omega for weakly finite deltas, then there is, and we are using this norm-based hierarchy, then the result transforms into a triviality. Okay, so first we have this norm-based slow-growing hierarchy that is defined analogously to our previous hierarchies. So basically, now instead of saying, so basically you can have this uniform definition where G alpha of x is like this maximum G bit of x +1, where normal bit is less bounded by x and bit is less than alpha. So it's kind of the same style of definition. Yeah, so and so naturally, of course, G alpha could be extended from a functor, extended to a functor from natural to natural, and further from to delta. And in fact, if you apply it to the same tree and kind of associate ordinal, so d of omega with d for weakly finite delta is d, then you could construct gd. But in fact, what happens is gd is simply just d. It's kind of basically one need to look carefully at the definition. But what happens basically is this slow-growing hierarchy in effect it just behaves like an identity transformation of this weakly finite deltas. Yeah, and so essentially it becomes a triviality. And then one could so analysis of this hologram can become trivial. And and since we have the following result that if we basically here it wasn't really explained this stuff, but so basically one could choose this weakly defined delta such that d of omega is equal to epsilon 0, and the order of d omega will be in fact Pakhomov ordinal psi of epsilon omega to plus 1, and hence we recall this kind of norm-based counterpart of Gerard result, like more or less for free. Okay, so that's all.
Okay, thank you very much, Fedor. Thank you, Andreas. Any questions or comments for the speakers? Yes.
You get the other big five, for example, by restricting the level of alpha?
I think you could get AC0 and AT not like this. So basically, for appropriate alphas, basically you would see that this B alpha would behave like basically the point there is this classical result of Gerard that if X is AC0 is equivalent to the fact that for any valor to X, omega to X is valored, right? And then the point is like you could obtain something of the order of growth of omega to X as B alpha, and alpha actually will be quite small here. I don't remember what.
0 or 1 or
no, something slightly larger. I think maybe omega times 2. But
and the ATR naught would be
ATR naught would be ATR naught of course is equivalent to the totality of Veblen function by result. And then I think good question. So what exactly? What you exactly need to obtain? So I think something like omega to omega, but this. But I'm not exactly sure. Maybe it's small actually than omega to omega.
Andreas, do you know where that done function appears?
I think it's easy verification, but no one does.
Yeah, but we haven't carefully done it. But this is definitely But this is definitely
it should be around
case,
omega,
but I don't.
maybe a bit smaller.
The questions? Okay, so if not, let's think.